Welcome everybody to podcast 3 on chapter 20. It is on electrochemical cells. Electrochemical, please ignore this reference, chapter 14. I've taken it from the internet, this PowerPoint. I forgot the resource. I have to go back and check who the resource is, but this is not my PowerPoint. I am using a resource from internet. This PowerPoint is on electrochemical cells. And electrochemical, as the name indicates, these are cells that use chemical energy and convert it to electrical energy. So all your batteries, everything that powers your calculator, to your watch, to your cars, is a type of electrochemical cells. And you have already studied one type of electrochemical cell, which is Voltaic cell. And in chapter 20, Voltaic cells are spontaneous, meaning cell potential for those are positive. And if you're ever given question of two metals and they ask you which one should be made cathode, then the one with the higher reduction potential should be made cathode for the reaction to be spontaneous, or E0 cell to be positive. Now we'll be defining, again, just quickly going over Voltaic cell, but before that, let's zoom out a little bit and talk about electrochemical cells. Electrochemical cells convert electric energy into chemical energy or vice versa. And the Voltaic cell uses a spontaneous reaction to convert chemical energy to electrical energy. A battery is a series of two or more cells connected into series so that their potentials get added. So coming back to Voltaic cell, each Voltaic cell has two half cells, and in these half cells there's an electrolyte solution which is of ion of the metal of which we make the electrode. Now electrode is a combined term for cathode and anode. In the anodic half cell you'll have anode as the electrode, and in cathodic half cell you'll have cathode as the electrode. The electrons flow through external circuit from anode to cathode. It's important because if you mix the anode and cathode, then there'll be no flow of current because electrons will be transferred in between. So if you want the electrons to travel through external circuit, they need to flow, or the anodic and cathodic chambers should be separate from each other. Now a Voltaic cell is a little different than electric cell, but a Voltaic cell also has some common components as electric cell. It has electrolytes, it has cathode, it has anode, and electrons flow through external circuit. Now Voltaic cell is a type of electrochemical cell that spontaneously produces electricity by using a redox reaction. What is special about this redox reaction is it's spontaneous, or delta G for this reaction will be negative, or cell potential for this kind of cell will be positive. Remember, I will repeat it again. If you're given choice of two metals, then the higher reduction potential metal should be made cathode for a reaction to be spontaneous. So the reduction NOx and red cat, so reduction half reaction happens at cathode and oxidation half reaction happens at anode. An electrode is a common term for anode and cathode. Electrons flow from anode to cathode, and a Sol bridge is a porous boundary that separates the two half cells but still lets the electrolytes flow. And the purpose, if you recall, of this electrolyte is to maintain electrical neutrality, or they avoid charge buildup so electron transfer can continue. And then there was the shorthand notation of Voltaic cells. You write the anode first, followed by the electrolyte of anode, and then the electrolyte and cathode, followed by the cathode as the metal. And in between you write a double line, which is for Sol bridge. And this is a pictorial representation of a Voltaic cell. And these are various cells. A good activity to do here would be to calculate cell potentials of each of these cells, A through F. Why don't you guys take few minutes and refer to your reduction potential chart and calculate it based on the method that I had taught you in podcast 2. and we can compare the cell potentials in class. Now moving on to, we already did Voltaic cells in detail, so I'm not going to go over it because this is almost a repeat of everything you've done. But to write the half reactions, remember, even if you multiply a reaction by a coefficient, the cell potential does not get multiplied. So silver's reduction potential will remain the same for reaction without 2, and even if you 2 times the reaction, its cell potential will remain the same. So you don't double the cell potential. Now, can you tell me which way do cations move? Do they move to cathode or anode chamber? That is correct. They move to cathode because cathode chamber, the electrolyte solution in there, because its cations are gone, tend to develop a negative charge. So this positive charge goes there and neutralizes the buildup of negative charge. And similarly, anions move toward anode to neutralize the charge there. And this is a simple silver and copper cell. I would encourage you to calculate cell potential of the cell and let me know how much you find it. And moving on, this is the summary of Voltaic cell. And now you can skip this slide. There's some inert electrodes where the reduction oxidation happens a little differently, but we don't need to go over that, so we can skip that. Now standard cell and cell potentials. Remember, cell potential of a cell is reduction potential of the reduction reaction that happens at cathode and reduction potential of the reaction that happens at anode. Please note, even though at anode oxidation is happening, so typically the reaction will be written as Cu to Cu2 plus 2 electrons, right? But you will still look for its reduction potential in reduction table for this reaction, where it will actually be written as Cu2 plus 2 electrons gives you Cu. And you don't change anything, you don't change the signs, and I keep emphasizing that. So a positive E0 cell potential means the reaction is spontaneous. A negative cell potential means reaction is non-spontaneous. Now, moving on, these are some of the sample exercises for you. I would suggest that you guys take time, pause it, do each, and then check your answers from this. We will be doing some more of these problems in class. Now moving on to electrolytic cells. Electrolytic cell is a type of electrochemical cell which uses a non-spontaneous reaction to convert electrical energy, uses electrical energy to change it to chemical energy, which in turn generates current. So in a Voltaic cell, you used chemical energy to make electrical energy, but in electrolytic cells you will be using an external battery to drive the reaction because the reaction is non-spontaneous. But nothing much changes. Anox red cat still holds good. Reduction reaction happens at cathode, oxidation happens at anode, and reaction is not spontaneous. So the question that might come to your mind is, why do we ever want to deal with a non-spontaneous reaction? Why would we want to use external source of energy to actually make a chemical reaction happen? The answer is because sometimes you want to purify your metals, sometimes you want to do plating like gold plating, silver plating. For all that, you got to use external energy because these reactions are not spontaneous, but the outcome or the products of reaction is desirable, so we still want to invest energy and carry out the reactions. So electrolytic cell first of all has only one chamber. There are no two half cells, and in that you have a solution and there's anode and cathode, and electrons are pulled away from anode and pushed into cathode. As a result, anode acquires a positive charge and cathode acquires a negative charge, and this is the single biggest difference between electrolytic and Voltaic cell. In electrolytic cell, the polarity of anode and cathode is reversed. The other big difference is electrolytic cells have an external power source while voltaic cells don't. And lastly, electrolytic cells employ a non-spontaneous chemical reaction, meaning E0 is negative, and voltaic cell employ a spontaneous chemical reaction where E0 cell is positive. So if you remember, in voltaic cell, which metal did you choose to be cathode? The one with the higher reduction potential, right? By the same logic, if you had to choose a metal for electrolytic cell, you will choose the metal that has the lower reduction potential as cathode. So the reaction is non-spontaneous. Excuse me guys for my throat, I just have some remaining infection. So alright, so this is a good slide that compares voltaic and electrolytic cell, and you see the major differences are between the polarity of cathode and anode. In electrolytic cell, anode is positive, in voltaic cell, anode is negative. And the difference also is between voltaic cell using spontaneous reaction while electrolytic cells using non-spontaneous reactions. Now again, to write equations, nothing else changes for electrolytic cells. Okay, for writing equation, oxidation still is occurring at anode and reduction still is occurring at cathode, and I'll take an example and show you the reactions. And these are some of the sample problems for calculating. I'm actually going to go back to the PowerPoint, our class's PowerPoint, and I'm going to start here. So in electrolytic cell, you are often asked to calculate amount of metal that will be deposited or how much current will need to be passed and things like that. For doing these calculations based on electrolysis or electrolytic cells, you need to know two formulas. First formula is called QUIT. Q is equal to IT, or I is Q over T, where Q is the charge in coulombs and T is time. Using this formula, you can convert amount of current passed into charge if you know the time. The thing to remember here is time must be in seconds for this equation to hold good. So if you're given time in minutes or hours, you must change it to seconds, okay, because ampere is a coulomb per second, otherwise units don't cancel. So this is a diagrammatic representation of an electrolytic cell. Please note there is a single chamber there. There are two platinum electrodes, neutral electrodes, and there is this battery. When you make the battery, the longer plate represents the positive end. So this will be what electrode if it is electrolytic? Anode, and this will be cathode. Anox, red cat, so oxidation is occurring at anode, where two chloride ions are losing their electrons forming chlorine, and at reduction the electrons are being taken in by sodium ion to form sodium. So with time, cathode will grow in size because of the metal deposit, and anode will start dissolving. And this process uses electric current that comes from the battery. The battery literally pulls the electron from anode and pushes them towards cathode. And there is no salt bridge here. So this is an electrolytic cell. In an electrolytic cell, you can use quantitative analysis, quantitative methods to figure out how much of metal would be deposited or how much current you have to pass. An example of such a problem is a current is passed through electrolytic cell containing NaCl for 1.5 hours. Write the electrode reaction. So first thing, you'll have to write NaCl's reaction, then you have to calculate mass formed at each electrode. So first you have to write oxidation reaction at anode and reduction reaction at cathode. Now for figuring out the mass, the process is using Q is equal to IT. You'll calculate the charge, okay, uppercase Q, I wrote lowercase q. You can calculate charge, and then charge you can use Faraday's constant. 96500 coulombs is the charge that 1 mole of electrons carry. And using this conversion, once you know how much charge you had passed, you can figure out how many moles of electron would have passed. And you know that 2 moles of electrons are released here to deposit 2 chloride ions, and 1 mole of electrons taken in here, and using that mole ratio you can figure out the mass produced at each electrode. Let's do the problem. So first step is to calculate charge. Remember, the time in charge must be in seconds. And then once you have charge, then use Faraday's constant. 1 Faraday is 1 mole of electron, and 1 mole of electron deposits 1 mole of sodium. Why? Because it's Na plus electron gives you Na. So 1 mole of electrons will deposit 1 mole of ion, and then you get mass, and that's your answer for sodium. Note, for chlorine it's 2, or you can write it's pretty much eating one step. 1 Faraday is 1 mole of electron, and you need 2 mole of electron to deposit 1 mole of chlorine, or you can just write it as 2 Faraday, and that gives you 0.90 grams of chlorine. So that's one type of problems you're asked to calculate. The second type of problems you're asked to calculate is they might ask you which one will evolve first if there are multiple gases, or what will deposit on cathode. So if you have a mixture of solution that you're electrolyzing, you got to see what are the players on cathode and what are the players on anode, what can be released or deposited. And from there you can compare the reduction and oxidation potential. The highest reduction potential will get reduced first, the highest oxidation potential will get oxidized first, or lowest reduction potential will get oxidized first. So if you have a mixture of copper chloride, zinc chloride, and obviously it's aqueous, so there's water in there. So there are 3 cations: copper ions, zinc ions, and water. Remember, water can either accept electrons or lose electrons. Then chloride will not be reduced. Can you tell me why? You're right, like charges repel each other. It's already an ion, it wouldn't tend to accept electrons, and reduction is acceptance of electrons. So if you compare the reduction potential, which has the highest reduction potential, copper. So copper will be reduced first. Okay. Then for oxidation potential, you got to see what can be oxidized, chloride or water, and compare the oxidation potentials. And oxidation potential of water is more, so oxygen will be present or released. And then the last slide is about electroplating. You've often worn, gold-plated jewelry, silver-plated jewelry. Have you ever wondered how they form those? That jewelry or spoon is formed by making cathode of the article that you want to plate, and make anode of what you want to coat, and then put the aqueous solution of that ion in there. In this case, we want to coat our spoon with silver, so we'll take silver anode and put some silver nitrate solution in there and pass electric current. Silver ions will go and deposit one by one in a smooth layer by accepting electrons at the cathode, and this spoon soon will transform into beautiful silver coated spoon. And that's electroplating. And that's the last podcast of the year. Thank you for all your patience with me this year.